Hello everyone and welcome to Control Engineering and Control Theory tutorials. In this tutorial, we explain how to properly compute an impulse response of a state space model in MATLAB. Let's immediately start. Over here, as a test case, we consider a simple spring mass damper system. The system consists of a box with a mass of m that's connected by a spring with the spring constant of Ks and a damper with the damping constant of Kd to the wall. We assume that there is a force F acting on the mass, and the force F is the control input. Over here, we introduce the variable x. The variable x is actually a displacement of the box from its equilibrium point. By applying Newton's second law, we actually obtain the dynamics of our system. And this ordinary differential equation represents the dynamics. Again, m is the mass, Kd is the damping constant, Ks is the spring constant, F is the external force, x is the displacement, x dot is the derivative of the displacement with respect to time, or it is actually velocity. X double dot is the second derivative of x with respect to time, that is x double dot is velocity. From this equation, we can express x double dot like this. The next modeling step is to introduce the state space variables. We introduce a new state space variable denoted by x1. And we assign to x1 x, that is x1 is equal to x. The second state space variable is denoted by x2, and we assign x2 to x dot, that is x2 is equal to x dot. Now, if we differentiate these two equations, we will obtain the following. From the first equation, we will obtain that x1 dot is actually equal to x dot, and from the second equation, we can see that x dot is equal to x2. And this is our first state equation. If we differentiate the second state equation, we will obtain that x2 dot is actually equal to x double dot. However, our dynamics tells us that x double dot is equal to the right-hand side given over here. Now, in this right-hand side, instead of x and x dot, we can write x1 and x2. So let's do that. From this equation, we obtain that this is equal to minus Ks over m multiplying, instead of x, we write x1. Then we have minus Kd over m multiplying x dot. Instead of x dot, we write x2. Then we have plus 1 over m multiplying f. Now, in this equation, instead of f, we will write u. That is, here we will assign f is equal to u. And finally, we can write our second state equation that reads as follows. x2 dot is equal to minus Ks over m multiplying x1 minus Kd over m multiplying x2 plus 1 over m multiplying u. And this is our second state equation. And finally, we are ready to write our state space model. To write a state space model, we first need to introduce the state vector x. And I will denote it like this, x underline, to distinguish it between the displacement x. That is, when you see x underline, you know that this is actually a vector. And the state vector consists of the state variables x1 and x2. These two equations, that is this equation and this equation, can be written in the vector form like this. We will have the following. We will have x1 dot x2 dot is equal to, then we will have a matrix multiplying a vector x1, x2 plus we will have a vector over here multiplying u. So let's see what is inside of this matrix. From this first equation, we can see that x1 dot is x2. Consequently, here we'll have 0 and we will have 1. On the other hand, from the second equation, we can see that over here we will have minus ks over m, and over here we will have as a second term kd over m. Let me just write this nicely so you are not confused. I'll have minus kd over m as the second term. On the other hand, from the first equation, we can see that we will have 0 here, and we will have 1 over m here. Let me again write this nicely, 1 over m. And this is our state equation. Now, this vector over here is x underline dot. This is our state vector. This matrix will be called as the matrix A in our state space model. This vector is x underline, that is a state vector. This matrix here, which is actually a vector, will be called as B. And finally, this is our input. On the other hand, to conclude the state space model, let me just write like this part, such that you don't get confused. Let me just increase this. And finally, we need an additional equation. That's our output equation. Over here, we will assume that only x is measured. Consequently, the output equation will look like this. 1, 0, multiplying x1, x2, plus 0 multiplying u. This equation tells us that we are actually only measuring x1, and y is the output. That is, y is the measured variable. This row matrix will be called as C in our simulations, and this zero matrix will be called as D. Consequently, we have defined a state space model in the standard form. X dot is equal to AX plus BU, and Y is equal to CX, let me denote it over here, that this is also an X, plus D times U. Okay, now we are ready to simulate this system in MATLAB, that is to compute its impulse response. Now, but before we do that, let's explain the significance of the impulse response. What is an impulse response? Well, the impulse response is obtained by putting an impulse function over here. Let me illustrate that. Over here, for the time being, I will erase everything except the things that we need to illustrate the impulse response. So we don't need this thing anymore. And let's explain the impulse response. So what is an impulse response? Well, impulse response from a mathematical point of view looks like this. This is the time axis and this is the force F. Now, let me just change the color so you can clearly see what the impulse function is. The impulse function is mathematically defined like this. Before 0 time instant, it's 0. Here it is, it's 0. For values of time larger than 0, it's also 0. However, initially, at time 0, the impulse function assumes an infinite value. We usually denote infinite functions like this. So what happens over here? The impulse, f, is 0 for t smaller than 0 and for t larger than 0. At 0, actually, it assumes an infinite value. Of course, this is a mathematical abstraction since you cannot make the force to be infinite at one point. However, in practice, you can imagine that you take a hammer over here and that you basically hit this mass from either this side or the other side with a hammer. That is, you can imagine that you have a hammer and you hit suddenly this thing with the hammer and you remove the hammer, and this will give an impulse. Or you imagine that you push with your hand this mass, and the response of this system will most likely look like this. It might also have oscillations, it might also have different phenomena. However, if the system is damped very well, x over time will most likely look like this. It's going to be 0 initially, and then at the moment you put an impulse, you'll see that x is actually doing this. And then it might oscillate, and if the system is stable, it's going to settle to 0. And this is actually an impulse response. If you see such an impulse response of the system, you know that the system is asymptotically stable. That is, it's going to dissipate the energy. From more general point of view, the purpose of the impulse response is to investigate stability and to see how fast your system will dissipate the applied energy. Okay, let's start with the MATLAB modeling. First, let's clear the workspace and let's use CLC to clear the previous history from the command window. Okay, the next step is to define the model parameters. Over here, I will assume that the mass is equal to 1. The spring constant is equal to, for example, 1000. The damping constant is equal to 10. And that's it. Next, let's define our system matrices. Here's the matrix A. The first row is 0, 1. And in the second row, we have minus spring constant over mass. Then we have minus damping constant over mass. Then the B matrix is 0 in the first row, and in the second row it is 1 over m. Okay, the C matrix is 1, 0, and the D matrix is 0. Okay, let's continue. To define a state space model in MATLAB, we use the function SS. And over here, we need to specify the system matrices. We specify A, B, C, and D matrices. And this will return our state space model. I will call it SS model. Okay, let's apply this and let's evaluate and let's see the result. And let's analyze what's written over here. We can see our state space model. Here it is. A matrix, B matrix, C matrix, and D matrix. And this is a continuous time state space model. The next step is to compute the impulse response. To compute the impulse response, we will use the function impulse. And we specify our SS model as the input argument, and that's it. Simple as that. So let's evaluate this. And here is the graph showing our impulse response. We can see that the impulse response decays over time. This means that the system is asymptotically stable and that the energy is actually dissipated inside of our system. This is mainly due to the damping that exists in the system. Finally, over here, we need to do one more thing. Namely, here we just computed the impulse response. However, in many applications, you would like to get the time series of the impulse response. So let's do that. But before we do that, let's first define figure 1. So the impulse response computed directly by applying impulse and plotted will be on figure 1. And over here, let's extract this impulse response. We can extract the impulse response by simply defining the output and the time of simulation, and the impulse function will actually return yi and ti. And again, as the input, we specify our state space model. That's it. Okay, after that, let's first execute this, then let's continue. And here I made an error, should be impulse. Okay, be careful. And you can see in the MATLAB workspace, if you type whos, you can see yi and ti, and they are ti actually, and they are time series. That is, yi represents the impulse response and ti represents the time. Okay, let's now plot this extracted impulse response. Let's define figure 2, and let's do plot ti, yi, and that's it. Okay, let's see the result. And over here you can see that the two graphs are identical. This means that we are able to properly extract the impulse response time series, and later on you can do some additional analysis by using this time series. Okay, that's all for today.